Good afternoon, class. It just got a little quiet, so I'll take advantage of that. Let's get started. A few things I want to get through today. I've been meaning to get through something that I brought up last class called optics and some good examples of optics, like how telescopes and cameras work. I do want to get to that today. I want to address a couple things that have come up the last couple classes before that. First, and so here's your warning, there's going to be an eye clicker in a minute. But before we do that, I just want to reiterate a quick point about fluorescent tubes. There was a question last class. Why do we use mercury in this complicated process of going from ultraviolet light to visible light? So if you remember, the way the fluorescent tubes like the ones in this room work is we humans have finally decided just getting something crazy hot to make light, that we could probably have a more efficient system than that. So up here, we're going to use these lights again later, but up here you'll see some examples. This is an incandescent bulb. This is just a filament with enough electricity running through it that it gets so hot it glows. Not efficient. Gets pretty warm. A lot of the light coming out of here is wasted as heat. I have two other examples of fluorescent tubes. You can see that they are both fluorescent. Both of them have mercury gas in them. Both of them are coated in phosphors. Those phosphors convert the ultraviolet light from the mercury to a frequency we can see. And you can see pretty clearly, I think, maybe from where you're seated, hopefully you can see. Those end up in two different color temperatures. And I mentioned last class that we often refer to color temperature. And that's just kind of the blend of red, green, and blue you get out of certain combinations of phosphors and LEDs and things like that. We humans are pretty used to seeing things that glow due to heat, our own sun or fire, things like that. So we're kind of familiar with warm glows and cool glows, which are actually, now that I think about it, those are actually kind of reversed. Something we kind of consider warm is cooler. Something we consider more cold, like more bluish and purple, that's hotter. But anyway, so I think this one right now is looking a little bluer, and this one's kind of yellowish, orangish, pinkish. So the question was last class, why do we go through this complicated process in fluorescent tubes of sending current through mercury vapors? Mercury is a dangerous chemical for humans to touch. Why do we have liquid mercury and then vaporous, gaseous mercury inside there? And then we light that up, and that emits light that's not really visible to us, and then we convert that. We kind of step it down into something more visible. I was doing a little bit of research yesterday and today. The answer is that's just the best we've come up with. There have been some attempts to replace the mercury, but it's just a pretty good system, and so far we haven't been able to come up with something mainly in terms of price and efficiency. Efficiency is the big one. So one of the main reasons we want to move away from incandescent bulbs to things like fluorescents, eventually we're going to get rid of fluorescents and go toward LEDs anyway, but the reason we want to get away from them is just literally efficiency. So how much electricity does it take to light up a room or something like that? And we've come up with this mercury process that is just pretty efficient and works pretty well. And so mercury is a metal, but at room temperature surrounded by some noble gases, it'll become vapor, and we can ionize that and get current running through it, and we can convert that. We can get some pretty high energy out of that gas. That's kind of what we're shooting for, is high energy. Convert that down to something visible, and we can all see it. So long way to say that's the best we've come up with. Not ideal because, hey, it's mercury, and we'd like to not have mercury in our ceiling, but it's efficient, I think, is the best answer to the question. Okay, we might get to 3 eye clickers today. Let's start with number 1. Here's our first eye clicker for the day. Total change of subject. We'll see why I'm bringing this up. Total change of subject. The question is, how does the internet get across the ocean? If you Google is based in America, and if you're not in America, you can still Google stuff. How does that happen? Well, unless you're in China, it's filtered, I think, or North Korea, you probably can't Google. I don't know. But a lot of places you can Google. How does that work? Is the question. A, satellites. B, direct radio transmission. C, microwaves. D, gamma rays. Or E, big fat wires. All right, take about 10 more seconds. Okay, if you just walked in, we will still have some more eye clickers. You're good. But I just stopped that one. So I was just up here Googling. I Googled telecommunications just to see what comes up when you Google telecommunications. And all this stock footage has things like satellite dishes and antennas. And oh, can you see that one right there? This one, the cell phone in space going boop boop. Stuff like that. That's what happens when you Google the word telecommunications. I blame that for the fact that we mostly got that one wrong. I blame these types of images. So if I want to, I don't know where we got this idea that we need to beam stuff. I mean, we have telecommunication satellites. Back in the day, your parents used to pick up a phone and call long distance to grandma or whatever, and that might have bounced in space. We've actually, I think the main reason we don't do that anymore is just we have too much data. We're not making, audio calls don't require a ton of quality. When you're talking to grandma, you're not that concerned. You can hear all the nuances and the frequencies and the timbre of her voice. But when we're transmitting Netflix just all day long, we need better data rates, bandwidth than that. So here's how we do it nowadays. We shine light. We shine light through plastic tubes. So I'm gonna turn on this camera right here just so you can see that. Let's see. Let's do the side projector. So by the way, I've got my tube. I've got my bowl of cooking oil here again. We're going to use it for something different today. So here's my tube. Here's my, the internet is a series of tubes, right? Here's my tube, and here's a nice green laser. You can see my laser dot there. So I've got a green laser. This is a laser. Lasers are light. This is photons. They are crazy fast. They go 300 million meters per second. That's nice. We can take advantage of that. And visible light has a frequency of something in the terahertz region. So we're talking trillions of times per second. So I can cram a ton of data into visible light. And I can route it. You can see the top here. Whoa. Backwards. There we go. So you can see what I'm putting on camera is the other end of this tube. So I've got this nice acrylic tube here. I can actually bounce light through this tube. And this tube is sort of like I can kind of hang on to it. So I can route it. So I want my light signal. Right now, my light has to go in a straight line if I do this. So if you were to get in the way between me and where I was trying to shoot the light, it's not going to work. There's something in the way. But I can route light through plastic like this. And this is called fiber optics. And so fiber optics works by something, and here's how fiber optics works. I can shoot light through a clear medium. It needs to be clear. It needs to be transparent to light, so light will go through it. And a key is I need a difference in refractive index between the stuff and the stuff on the outside. And so what we're getting here is total internal reflection, which I've mentioned a couple times in this class. We're getting total internal reflection, meaning the light stays inside the medium. And the way you get total internal reflection is you need two different media. So right now it's air and acrylic. So I need two different media. If I just had air, I'm not going to get total internal reflection. One cool example of that is the reason we used my cooking oil a couple classes ago was cooking oil has about the same index of refraction as acrylic. And so if you remember, I stuck a piece of acrylic in my cooking oil, it became invisible. And the reason it was invisible is light was passing through air, then Pyrex, then cooking oil, then acrylic, then cooking oil, then Pyrex, then air again. And the light just was unbent because we have the same, at least it was unbent as it was going through Pyrex, cooking oil, and acrylic, because it has the same index of refraction. And so right now, I think the bowl and the cooking oil are pretty visible because I'm getting refraction from air into those media. But if inside there's like a bunch of, I don't know, there could be a bunch of objects in there right now, all of the same index of refraction. I can't see them. seeing things, I rely on it doing something to the light, bouncing it, refracting it, changing its color, something. So I can, yeah, for all I know, there's a bunch of acrylic little people in there. Okay, so if I were to dunk my tube, my fiber optic in there, so let's see, let's go back so we can see the end. If I dunk the end, let's see. If I were to dunk any portion of the tube into the acrylic, so right now, let's see, there we go. If I were to dunk any portion of the acrylic into that oil, I stop getting a signal. So right now you can see the end. The end is that circle of light right there. The end is that circle of light. If I dunk, I'm not even dunking the lit part, I'm just dunking like the middle. As I dunk the middle into the oil, I completely lose my signal because I'm not getting total internal reflection anymore. It's actually, you can see the bright spot on the table. Do you see that bright spot kind of in the middle of the signal? That's the laser leaving the acrylic and going straight into the table. It's lighting up the paper below it. So I'm actually losing my signal, and then if I take it back out, I get my signal back. So anyway, just a good example of tonal internal reflection and the fact that it requires a difference in index of refraction. Okay. So long story short, that's how we get data across oceans right now. We have big fat cables. The answer is E, big fat wires. And we figured out a long time ago, again, I think it has something to do with the fact that we need to be now streaming HD Netflix all day long. That's a lot of data, and trying to do that via satellites can be done. I mean, if you watch any, like, I don't know, adventure show or something, they've got sat phones, right? So sat phone is a phone that directly talks to a satellite and then is beamed back down to Earth. There is telecommunication satellites, that's for sure. But a lot of the data we now use just literally goes across wires. So it's kind of like we've stepped back a little bit, you might say. So right now, if you were to get on your phone and, I don't know, send a text message or get on Facebook or something, your phone is not connected via wire probably, so that part has to be wireless. So let's say you're using cell data. So right now I get my phone out and I use cell data. My phone is actually blasting photons through the ceiling of this classroom, out of the physics building, and it's omnidirectional. My phone doesn't know where the cell antenna is and blasts it in one direction. It just goes, and it blasts out in every direction. Some cell tower, maybe a mile from here, is just sitting around waiting for your cell. There's a tower with your carrier. So say you're a Sprint customer. Sprint has stuck an antenna up on a tower somewhere a mile from here. So your cell phone is just doing this, blasting waves in every direction. There's an antenna a mile from here that goes, oh, hey, that's someone trying to access Facebook. They get that signal. That's the end, really, of the wireless part, though. So the cell antenna gets your request, hey, I want to see Facebook. That sends it down a wire. That goes, I don't want to get into how the internet works, but it goes over wires to a big, literally a computer in a building somewhere. Facebook owns just big buildings full of computers, and your Facebook page is a file on a physical computer. Not to get too much into how the internet works, but yeah, I think this whole idea of the cloud, we all think that the internet is just it's space or something. It's not. It's just warehouses of big fat computers sitting in big warehouses like in Utah somewhere. And so there's your Facebook page is sitting on a computer somewhere, and I say, and so you want to see your own Facebook page for some reason. So you say, I want to see my Facebook page. A lot of that is over the wires, and then the server there goes, okay, you can see that, sends the page back, and it goes up the antenna to that same cell tower a mile from here, and that blasts it. It doesn't know exactly where you are. It knows you're closest to this antenna, so it blasts it out of that antenna. It doesn't blast out like every antenna in the country hoping just to get you. It knows where you are. Your phone knows where you are. It's a good thing to remember. Therefore, NSA knows where you are. But so that blasts out all over the place, and then it comes back down to your phone. But most of that is wired. Most of that is not wireless. And it's a similar picture if you're using Wi-Fi. So if you're using your laptop or your phone on Wi-Fi, between here and the router, I keep looking for the router. There's two of them. So between your phone and the router, that 100 feet, that's wireless. But that router is connected via Ethernet cable to another hub somewhere at UVA. And then within a short distance, UVA is hooked up to one of the better internet connections. So within a short distance, it is on a big fat cable running across the United States. And if you're trying to get data to the other side of the ocean. It's literally going to the beach, going down, going across the ocean, coming back up to some other port city, and back out to some server. It's that, what was that? It is that rudimentary, you could say. I stole a picture off the internet of, there's some of the networks. So there's some of the cables literally just running under the sea. And here's one of them coming out. So it's literally just that. So if next time you're at the beach, you see like a manhole, that could be the internet coming out of the ocean. It's that kind of basic. So I don't know, the idea with the cloud, that everything's up in space and something, it's cables mostly. It's wires. And one other very side note, I'm getting off on tangents, but one other side note, it happens very fast. It happens at roughly the speed of light, which is nice, the speed of light in this material. And so you can cram a lot of data in there. So it's literally just flashing a laser on and off. So it's digital, so it's just ones and zeros. And those little flashes happen very, 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 very fast. And what's cool is I can actually cram a lot of data into a wire, more than I can just with one laser, because I can actually send different wavelengths. So I can send several colors of laser all through one cable. And on the receiving end, thousands of miles away, the signal is not diminished much. I forget how, like every 500 miles or something, they have a little amplifier down at the bottom of the ocean. But then it's literally just flashes of light, and then I can do different colors. And I can cram tons and tons and tons of data, like terabytes of data into something about this big. It's pretty impressive system, but it is still cables. It is very fast, but it is finite speed, and physicists are working on how to make it faster, but we're dealing with light, and so while we're still dealing with light, we're going to be stuck with that speed. So getting from here to the other side of the ocean is going to take milliseconds. You may have heard that real estate closest to the stock exchanges went through the roof a few years ago once people realized literally the length of wire between my computer trying to do micro trading at nanosecond speeds, literally the length of the wire mattered. And so something would happen in the markets, and I could take advantage of it 1/billionth of a second later than the guy that was 1 foot further away. And so there was literally this race to get closer and closer to the stock exchanges, because every foot bought you 1/billionth of a second. So you wouldn't think trading would happen that fast, but that's how trading happens now. Another myth is like the guys all in the pit going, trade, sell. That's not how the stock market works anymore. Those guys still exist, but most trading is happening automatically via computer, right? There's probably a movie about that. I don't know, Big Short or something. No, that's different. But yeah, so it's computers doing it automatically, and it's happening in billionths of a second all day long. And so it's crazy that computers have had to get closer and closer and closer. And in fact, to try to regulate that, they even started changing. If you're here and your neighbor's computer's here, they made your cable just a foot longer, just so you wouldn't have an advantage over the next guy. It's nuts. But anyway, it happens at the speed of light, and that global gambling arena has gotten out of control as a result. Okay. Tangent. Here's another tangent, and then we're going to get on to optics. Someone asked this at the end of last class. I thought it was a really good question, because we've been talking about heat in this class. So I did want to just quickly give here's your eye clicker for the day. What is cold? I thought that was a really good question. Somebody asked me that at the end of last class. And so here's our options. I've got 4A, when photons decrease in energy. B, when photons of lower frequency than infrared. C, energy transfer from a high temperature system to a low temperature system. Or D, a subjective perception. Let's take 30 more seconds. Okay, 10 more seconds. Okay, good. I did not stump that many people. It is a subjective perception. It's D. And so It's not really a thing. Kind of like centrifugal force is usually not a thing. It's usually just a perception. I can push somebody centrifugally, and then there it exists. But it's usually a perception. Cold is usually a perception. Answer C, energy transfer, that's the definition of heat. The definition of heat is energy transfer from between two thermal systems. That's the definition of heat. So heat is a real thing. That's the transfer of energy. And so if you've ever been near something hot and put your hands up to something hot, most of that heat is actually photons hitting your hand, and you perceive that as hot. All of us, and we've said this before, like black bodies, all of us are emitting heat right now. Heat is a real thing. It's energy leaving your body as photons, and it's in the infrared. So when I put my hand up to a fire, what I perceive as heat, that's infrared photons. Cold is just what humans perceive when heat leaves them. And so if I walk out and I say, "Brr, it's cold outside today," all I'm doing is I'm measuring the amount of heat leaving my body. And so my body is trying to stay 98 degrees. And if I'm in an environment where it's around 98 degrees, I'm going to be in thermal equilibrium. Now, since I'm generating heat all day, sitting in an environment where it's 98 degrees is not comfortable, because I'm actually generating heat. My metabolism, all those chemical reactions in my body create heat, so I want to get rid of heat. So I need to be in an environment less than 98 degrees in order to transmit heat. And so if I'm 98 degrees and the environment's 98 degrees, I'm in thermal equilibrium with the environment, I can't get rid of heat, so I need to sweat and do things like that. But if I'm in an environment less than 98 degrees, I can transfer heat to that environment. And if it's like 70, I'm happy with that. I'm happy with the amount of heat transfer. I'm creating heat. I'm getting rid of it at a nice rate. I'm all happy. I walk out and it's 0 degrees outside. Heat starts leaving my body faster. The rate of heat transfer has to do with the difference in temperature. And so if it's hot, if it's like 0 degrees outside, I'm losing thermal energy. I'm getting cold. And so my perception of cold is just the rate that happens, the rate at which heat leaves me. And then if I go somewhere where it's much warmer than 98 degrees, I'm getting heat going the other direction. So heat always flows in the direction of hot to cold. So if I'm the cold one, I'm going to be getting the heat. And I might not be able to dissipate that, and that's bad. One interesting experiment you could try, I think all of our seats have like metal on the sides. Yeah, okay. So right now this room is by definition room temperature. Whatever the temperature of the room, we call that room temperature. It's like maybe 70-ish degrees. Therefore, anything not producing its own heat is at room temperature. The floor is at room temperature, the air is at room temperature, the ceiling, the walls, your chair are all at room temperature. Now, if you've ever, that was surprisingly not, yeah, fiddle around with the stuff on your chair, you might be able to touch something that feels colder. I think you know that metal usually feels colder, right? So you go outside, what was I doing this morning? I don't know, just touching my car felt colder than touching like maybe something plastic. So I think we're all familiar with that phenomena that metal things are colder. Right now, if you were to touch something in this room if you were to touch something on your chair that felt colder than some other part of your chair, that is totally a perception. All the parts of your chair are at room temperature. All the parts of your chair have been in this room long enough. They're probably in thermal equilibrium with the room, and so they're all 70 degrees or whatever. The only time something feels cold, two things at the same temperature feel colder, is if they increase the rate of temperature of heat transfer. And I mean the fancy term for that is thermal conductivity. So certain things certain parts of your chair, the metal parts of your chair, they're metallics, they have free electrons. They have a higher thermal conductivity, and by touching them, heat's going to leave me faster. So I can actually touch two things that are the same temperature. I'll perceive one as colder just because it's a higher thermal conductivity. Okay. Oh, wait. Well, okay, speaking of heat, I was going to do let's do one more quick example, then we'll talk about optics, promise. Yeah, 20 minutes left. Question? a good part. Yeah, so Caitlin asked, so yeah, and when you get in a car in the summer, there's certain parts of your car that are way hotter. Well, so I have a black car with a black interior. So my steering wheel is sometimes just can't even touch it. So that has to do, well, let's see, my old car had a black steering wheel that was plastic. So black absorbs more light. So it's my car is, the sun is going through the windshield and is being absorbed by the black car and the black interior and the black steering wheel. So black absorbs heat. So that my whole car is getting hotter. Now, my old steering wheel was plastic, and it has a very high thermal conductivity. So there's two things. The black was absorbing a lot of heat, and when I touched it, it had a high thermal conductivity, so more heat transferred to me. Now my new car has a leather steering wheel. That sounded fancy. It's not. It was an option. But that leather has it's skin, so it has a lower thermal conductivity. So even though they might be the same temperature, leather has a lower thermal conductivity, doesn't feel as hot. Now your seatbelt is like, you can burn yourself on your seatbelt, and what's going there is, yeah, that's just a very high thermal conductivity. So inside your car, silver is actually more reflective, and that's a good transition to what we're about to do. Silver is actually reflective, so it should be a little bit cooler. But because it has such a high thermal conductivity, yeah, it's gonna zap you good. Yeah. So metal things are gonna feel really, really hot. Where's this guy? Okay, one quick example of that. This is a great example of bad physics. I think the first time someone demonstrated this gizmo to me, I don't know if you've ever seen this gizmo before. It's called a Crooks Mill. The first time someone demonstrated this to me, they said, "This is awesome. Look, you can actually make it spin with light." And let's see, where's my light switch? You can make it spin with light. And so if I shine a light on it, it starts spinning. Which is crazy. And it's inside a near vacuum. It's inside a near vacuum and it's closed, so it's not like I'm pushing on it. So the explanation is, I just was spinning it with photons. I was actually bouncing photons off of it and getting a momentum transfer, and I could spin it, which actually is physically possible. There are experiments you can do, much more expensive than this one, where you can get that to happen. I don't know, you may have heard of solar sails. One way we hope to someday get to far, far planets is we can erect a big solar sail, just like a sailor would sail. But instead of using wind, we're actually using momentum transfer of light. So I can make a spaceship and go out in space and hold up a big sail, and the sunlight will actually cause me to fly through space, cause me to accelerate. And what's actually happening is I'm getting a momentum transfer as photons bounce off that sail. But that is so, so, so tiny. It's so hard to do in an environment like this. This thing's not perfectly balanced. There's probably not a perfect vacuum in there. In fact, it's definitely not a perfect vacuum. What we're seeing here is similar to that question about seatbelts and cars and stuff like that. I don't know if you can tell. These little veins on here are black on one side and silver on the other side. And so what's happening is when I shine light in there, the black holds on to it and gets a little warmer. The silver reflects it and stays a little cooler. So I now have veins that are hot on one side and cold on the other. That's half the story. The rest of the story is there is a little gas in there. It's not a perfect vacuum. So as gas molecules hit the hot side, there's more of a momentum transfer because the hot side has a lot of thermal energy. So when gas molecules hit it, they leave at a higher velocity. And so the gas molecules bouncing off the black will have a larger momentum transfer than the gas molecules bouncing off the silver, which is a little cooler. So what it should do, if that explanation is correct, you should see it go this way, due to the gas bouncing off the black. There it goes. So really all I'm doing is I'm heating the black side, and it's not like I'm bouncing photons, which would be really cool. I would love to be able to demonstrate that, but that's way harder to do. Way easier is just I'm heating the black side and it's spinning due to the temperature difference. Okay. Let's spend 15 minutes on optics, and then Friday we get to do electricity. Okay, let's talk about optics. Last class, yes, Julia. Yeah, good question. So Julia asked, what if there was less of a vacuum? Yeah, if I got all the air out of there, I couldn't do that experiment I just did. And the better vacuum, there's probably a happy medium. If there was a lot of gas in there, it would be harder for it to spin. There'd be air resistance. So there probably is a happy medium. There's a little bit of a vacuum. If I have too much air in there, it won't spin. If I don't have any air in there, it won't spin either because I have nothing to bounce off of it. So I probably just need a few gas molecules in there. It's less than, it's less than atmospheric pressure in there. There's a little gas is my answer. Yeah. Okay. We're going to run through some optics. That's all we need to do is one day of optics, I think. Then we'll be good. I'm going to lower the lights a little, I think. That's not lower. That's back to where we were. Let's lower. How's that? Okay. So here's my little beams of light. And so really what we want to talk about is just how we take advantage of refraction and reflection to do a few helpful things to us humans. So last class, at the end of last class, I lit the match from across the bench. And the way I was able to light the match was take advantage of the fact that just about I can manufacture a lens. Yeah, I was taking advantage of lensing. And a lens is something that just bends light to one point. It focuses it. So right now you're looking at a good example of a lens. It's curved, and so when the light hits, if the light hits dead center on that curve, that second one from the, let's see if I can get one to be straight. I'm trying to get one to be straight. If light goes, I can get light to go straight through because it's hitting at a right angle. But if it doesn't hit at a right angle, it's going to get bent, and I can use that to focus light. The mirror that I used to light the match had a similar property. I can use mirrors to focus light. And the distance between the center and where it's focused, that's called a focal length. So these mirrors have different focal lengths. That one's a really short focal length. And this one's a little bigger. Okay, and then I've got another lens over here. That one has a little bit longer focal length. So I can take advantage of that. So last class, up here's sort of a picture. What I did is I had a light source at the focal point. The light emerging from that mirror was all parallel till it got to the next mirror, and it was focused on the match. And I was able to focus all that thermal energy on the match, light the match. I want to run through a couple other examples of that. Our eye does the same thing, and so right now, your retina is, I don't know, maybe the size of a dime. If you want to see anything bigger than a dime, you need some optics. So your eyeball could work with just a hole in a retina. You wouldn't be able to see much with just a hole in a retina. I imagine the first creatures that had light sensitivity, that was maybe as fancy as it got. But we eventually developed this really great idea called a lens. And so your eye has a lens on the front, and what that can do is that can focus a lot of light down onto your retina. So what you're seeing there is I can see something kind of large over there on the left, like that big pencil, and I can see it by focusing it. Kind of like the mirror I have up here, like the lens I have up here. I can focus it onto my retina. Now, hopefully I think everyone already knows, I'm actually upside down right now in your retina. So your brain has to turn everything upside down, or right side up, I guess. And so right now, everything you've ever looked at was focused upside down inside your eyeball. And so there's an upside down me and an upside down that. Everything on your retina is upside down, and your brain has to flip it back around. They did an experiment, I forget where some scientists wore glasses that flipped everything upside down. So they were walking around, the ceiling was on the floor, and the floor was on the ceiling. And it took them, I forget how long, a couple weeks. Their brain just figured it out and flipped it. So they could walk around like normal, wearing these special glasses. They wore them 24/7. And then they took those glasses off and everything was upside down. And they had to wait for their brain to realize, okay, I'm not wearing the glass anymore. And it flipped it again. So your brain's just really good at that. It's flipping things when necessary. Takes a while. So that's what's going on right now. There's a very small me in the back of your eyeball, and your brain is flipping me upside down. Now, there's a focal length to your lens. And so if you want to see something at a certain distance, your lens has to squish. And there's little muscles in your eye that squish that lens and change its focal length. And so you can focus on things from different distances. I can focus on, something pretty close to me, and my eyeball has to bend my lens more if I'm looking at something close. Now, some people are farsighted or nearsighted. That just means their focal point is just behind or just in front of their retina, and then they wear glasses that adjust for that. So notice, right now I'm looking at something beyond the center of curvature of my lens here. If I move that pencil, notice if I move the pencil onto the center of curvature, I now have, oh, and by the way, I should mention what I mean by real. There's the image that's being created by this setup over here, your eyeball. It's a real image, and what I mean by real is you could put a little screen there and you would actually get a picture of the pencil. So right now, there is actually a little me in the back of your eyeball. It's real. It's an actual projection. It's an actual image. You could see it. So if you were looking at inside someone's eyeball, you'd see an upside-down version of everything they're looking at. Here's another real image. This is the same size because I'm sitting on the center of curvature, and if I move even closer, I actually get an enlarged projection. It's still a real image. That's what's happening up here on the screen. Right now, in the back of the room, there's a projector. That projector has on it a small version of that projector, and it's upside down. And so everything inside the projector is, like an inch or two large, and it's upside down. And it's being projected out through a lens and being focused way up here. Now, if you've ever focused the projector, you know you actually have to focus it. So if I were to move this screen a couple feet further or closer away, this would not be focused. So there's a focal point where that's happening. So when you grab the lens on a projector and turn it, or like on a camera, you're moving that lens further and closer away and changing where it's focused. Okay, so that's an example of a movie projector. It's a real image. It's still upside down, but now it's enlarged. Okay. If I bring my source of light to the focal point, it actually doesn't reconverge into an image. This is very similar to the headlights. The headlights was a source of light at the focal point of a mirror. Here's the source of light at the focal point of a lens. Very similar situation where the beams just emerge parallel and never come back. Flashlight and lighthouse, I don't know what other examples I can think of for that. Okay, so notice the last few images have all been convex lens. I'm way out here, then I'm on the center, then I'm closer, then I'm on the focal point. I have a real image, real image, real image, no image, and now if I move a little closer, what I have is a virtual image. Here's what I mean by virtual image. There's no place I can put a screen and get an image out of that setup. So the object I'm looking at is that tiny pencil to the right of the big pencil. The object I'm looking at is a tiny pencil. I put it really close to the lens. The light diverging from that small pencil, at no place does that refocus anywhere. So that doesn't seem too useful. But here's why that's useful. I can put my eyeball on the far side of that lens, and I will perceive a very large pencil. There's not actually a large pencil right there, but that large pencil I have on the left is what my brain is going to make up. And the reason my brain's going to make that up is I've drawn dotted lines. So if I'm on the far right of this, my eyeball's on the right side of that lens, right? When you're looking at something with a magnifying glass, you're on the opposite side of the lens from what you're looking at. And so when my eyeball's on the right, my eyeball is going to get hit by these photons, and my eyeball is going to do what it always does. It's going to say, oh, those probably came in straight lines on the way to me. And that's false. The lens bent them. But my eyeball is going to kind of trace them backwards, and that's those dotted lines. And it's going to perceive a large pencil or an enlarged image of whatever you're looking at. That's a magnifying glass. That's how a magnifying glass works. Just your brain getting hit by photons that have been bent outward, and it looks larger. So I want to read small print on a very good eyesight. I can I'm basically taking those small words and bending them outward and making them bigger, magnifying them. Amazing. A zoom lens does the opposite. A zoom lens actually diverges light. I have one of those here. So again, I can make something look, it's actually diverging out, so it actually ends up looking smaller in this case. So the small pencil is what my brain is making up. the light is being bent out, and so my brain traces back in a straight line, and again, I'm perceiving something smaller. Okay. Let's see, we have 4 minutes left. I only have a couple more of these. We might get through them. Then, okay, so far up till now, everything's been lenses. We can also reform images with mirrors. And so eventually we're getting to with this is how telescopes work. Mirrors you probably know, are used in telescopes. I can recreate an image. If you've ever looked inside a spoon, you were able to see yourself. Next time you're looking at a spoon, you should be able to see yourself twice. Once from, depending on the spoon, once from like yay far away. And then if you bring the spoon closer to you, like this far, you're back right side up. So notice you're upside down inside the spoon, yay far away. Then you bring the spoon closer, you're right side up. And when you're right side up, it's like, if you've ever looked in one of those mirrors that makes your pores disgustingly large, that's how those work. That you put yourself really close to one of those mirrors, again, the light is being diverged, and there's a virtual image on the other side. So when you're really close to that mirror, it looks like you're really huge and on the other side. Again, that's your brain tracing those light rays back and perceiving a large image of you. And so in this picture, you're on the left side of the mirror. The thing you're looking at is on the left side of the mirror, and your brain thinks there's something on the right side of the mirror. In fact, maybe I should have even mentioned earlier, that's how, even like the normal mirror, like a flat mirror, that's how a flat mirror works, is your brain thinks there's a you on the other side of that mirror. So you're standing on one side, and your brain thinks there's somebody over there. There's a picture of that. So when you're standing on one side of the mirror, your brain, looks like there's another you twice the distance away on the other side of the mirror. Your brain's usually not fooled by that one. And then, because your brain is sometimes fooled, we have to put a little message on the mirror, on your passenger side mirror, that says, warning, objects in mirror may be closer than they appear. Because in the passenger mirror, we've bent that mirror out so we can see more stuff. So you want to be able to see not just a narrow sliver of sight to the right side of your car. You want to be able to see more. You want to be able to see into the blind spot. We can bend the mirror to get more of the blind spot, but you end up getting a similar effect like what we've been talking about with several of these examples. You get an image that is not truly representative of what's actually out there. You get something that looks further away. And in this picture, you can see things look smaller. The reason it looks smaller is your eye is making up that same geometry. Your eye thinks, oh, there's a small pencil there. And so when you look in the mirror and you see a tiny car, your brain goes, cars don't come that tiny. That car is probably just really far away. And so we have to put a little message on the mirror that says, no, it's not far away. It's a convex mirror. And then your brain reads it and then has to fight over what to believe. But hopefully that doesn't cause you to run over something in your blind spot. Okay. Let's do one more eye clicker, or we could call it a day. Looks like we're packing up. Let's call it a day. Okay. All right.